shot right there.
Went out of focus. All right. Stop messing around with the camera.
I mean, what class is that for?
I'm just typing up the weekly project work.
Gotcha. Cartwheel.
Yeah. You remember that time I limped in class? It still hurts. I can walk normally at least, but yeah, we're not to cartwheels and tumbles yet. We're
Visit the trainers.
I did.
Really?
He told me not to walk on it a lot, and then I didn't listen to that.
You should get one of those.
Hover around? Yeah. Yeah, but I do need a walker. Anyways, let's do a recap of this class. Okay, we talked about circuits. All right, we're gonna move on to what we're talking about today. No, I'm kidding. If we do a recap of this class, we've been through a lot already. This is second half of the semester. Second half of the semester, we do more stuff that has to do with this class. We started out this entire series talking about energy and power. Okay, energy and power are two very fundamental aspects of this course. Power is something that if you take control systems next semester, we talk a lot about power. Okay, why? Because everything is about power. Power is everything. This is why I sit in my office. It's a power move. No, everything here, everything in our known world is about changing energy, which is power. So it's all about power flow. In circuits, it becomes especially true because circuits is a really good hands-on way of understanding power flow. Once we talked a little bit about energy and power, we then went into resistance-only circuits. Now, the reason why we talked about resistance-only circuits immediately is because these systems are at steady state all the time. Even under the presence of a changing input source, the system is at steady state because it has no transitive behavior. Okay? There is no time delay. Resistance-only circuits, you get what you get. You don't have to do any integrals in order to calculate these. Okay? When we talked about resistance-only circuits, we talked about parallel and series. That was where we kind of introduced the concepts that components behave differently in parallel and series. Parallel and series components have a different relationship because of the relationship between current and voltage traveling through those components. Okay? Once we talked about parallel and series components, the next piece was we talked about equivalent resistance. What this allowed us to do was to simplify a circuit down and analyze it as if it were a single component and a power supply, okay? Which made things a little bit easier to look at. We also did talk about node voltage analysis and mesh current analysis. However, as I've said, I'm not requiring you to know that for this class because it does require a little bit of matrix analysis. It is really good information to know, but again, it's matrix analysis, so this is an introductory course, and I don't really want to teach you matrices that much. Once we talked about equivalent resistance, we then talked about what would happen if you put a power source in with this series, and here we got into Thevenin equivalent. Thevenin equivalent. Okay, so that was being able to model a resistance-only circuit as if two terminals are sticking out of it, and all you're doing is you're measuring the voltage across those two terminals. Okay. We also talked about superposition principle very briefly. We also talked about Wheatstone bridges and that sort. Now, after we had exhausted resistance-only circuits, we amped up the challenge in the class, and we moved into talking about both capacitors and inductors. Now here, we first started by focusing only on circuits that had capacitors and inductors in them, trying to understand the relationship between voltage and current traveling through these somewhat stranger components. From there, we moved on into first-order systems. In first-order systems, what we looked at was, well, we had RL and RC circuits. We looked at how the timing was influenced, and then we talked about the concept of transients. And when you have a behavior where a circuit is behaving one way, but steady state is a different behavior entirely. Okay? From there, we built off of this concept to talk about second-order systems. And then I sat around solving problems, and we had a good laugh. The world was good. And then we woke up. Okay. Any questions on where we've been? Because so far, everything in this class is built on the topics before it. You really had to understand energy and power in order to understand resistance-only circuits, because it was all about power. What we were doing is we were looking at power consumption in components. That was the relationship between voltage and current in all of these. Once we understood the relationship in power in here, what we did was we looked at a different component. Now, we also looked at parallel and series components. We did also talk about equivalent capacitance and equivalent inductance. We didn't get into these two, mostly because, again, the math gets really gross on those. But, I mean, we could have. I love you more than that. And then, once we talked about this, then the idea was, well, now what happens when we combine all of this to where we're at today? Now, what we're going to be talking about today is we're going to be talking about AC circuits. And when we do that, we're going to be continuing to build off of everything we've learned in this class so far to make it one step harder. Okay? I've had some students tell me that this is actually oddly one step easier than RLC circuits because you don't actually have to do integrals here, but we are going to be dealing with phasors, which if you like weird math, this is the class for you. Okay, so what is AC circuits? Well, to date, we have only discussed DC sources. Okay, DC sources being direct current and direct voltage. Okay. So if I draw my handy dandy voltage versus time graph, our DC voltage driven circuit looks something like this, where the power that is consumed is the integral of this with respect to the current. Okay? But it is actually a function of time. Now what makes AC circuits different is that AC circuits oscillate about a 0 point. And the power consumed ends up being an integral of the voltage differentiation with respect to the current. Okay? Basically, it's like an absolute value of the voltage. We have not yet dealt with an input source that has oscillated. I've given you exponential sources, I've given you linear sources. Most of the time we just deal with constant sources because those are far easier to calculate, and quite frankly most of the time you're not really going to be dealing with an input source that varies all that much. You're going to be dealing with a near constant DC series, so it makes the calculations easier. But things start to change the moment things oscillate. Okay? So, how do they change, Carol? Ooh, well, that's a good question. Huh? Let's get wavy with it. I feel like some surfer music is needed here. Rogers! Rogers! All right, so I'm going to I'm going to go ahead and draw an RLC circuit. Okay, now here this S-shaped source, it does stand for an oscillating input source. If you draw it sideways, it looks like this. Why does it look like that? Because it's a sine wave. That makes sense? So that's the symbol for an AC source. Okay, now when we plug this in, the solution method that we get stays the same. We do the solution for this. This is written in your book. You end up getting, like let's say we're solving for VC. You end up getting some d squared VC over dt squared plus 2 alpha dVC dt plus omega naught squared VC is equal to some forcing function. Okay, you end up getting the exact same system equation. This is what we're solving for. Once we have our system equation, we turn around and you have the exact same solution here. VC is equal to VCC plus VCP. That hasn't changed. Once again, you're looking at VCC, which is going to end up being some exponential function, which is A1e to the S1t plus A2e to the S2t, where this could be an underdamped system, an overdamped system, or a critically damped system. Doesn't matter. But your VCP is different. Okay? Now, when I introduced the concept of the particular solution, I said that the particular solution has to have the same time function as the steady state solution. Well, that poses a weird problem. We don't have a constant steady state solution here. In fact, we have an oscillating steady state solution. This is something where at steady state it's gonna bounce, because that's what it's gonna do. And that's kind of gross. So this has to have the same time function. So what we would say is, I don't know, maybe A2, well, A3 sine omega t plus phi. And that would be your solution. That's your steady state behavior. That's one way where it changes. Okay? The steady state behavior of this system ends up being a little bit weirder. And in fact, most of the time, when we look at AC systems, this part here, okay, yeah, it still exists, it's still valid. But most of the time when we're talking about AC systems, we really don't care about what happens right after you plug it in. This transient piece ends up being really short, but this piece here is the piece that matters. We do want to understand how the behavior of the system acts in steady state. And this part, I mean, that's just normal. Now the issue that comes in here too is that this piece has to go away. It starts at 0 and it ends at 0. That's funky. Now it isn't exactly, that doesn't mean that this piece entirely goes away, but what it does mean is that most people actually just end up ignoring it. And so will we. Okay. I told you we weren't going to do integrals when it comes to this one. We're not. We're going to play with something else that's fun. Okay, so let's look at one component at a time. Okay, so here's an AC input with a resistor. Here's an AC input with a capacitor. Here's an AC input with an inductor. Okay, and we'll go ahead and look at what the behavior of all of these are. Let's assume this is an AC voltage input. I don't actually know if there is an AC current input. I've never run into one. I've never even heard of one. So I'm not going to introduce that in this class. This is a voltage-driven circuit. Let's talk about the behaviors of each of these. First of all, in a resistance-only circuit, the circuit is always going to be at steady state. That's great. Okay, if we do KVL, we find that Vs is equal to Vr. According to KCL, we see that Is is equal to IR. Okay, that's fun. Science. Okay, but we know the equation for Vr. So that means Vs is equal to IR times R. And that's interesting. But we also know that Is is that. So we end up with Vs is equal to Is times R. I mean, that's all the math we can really do here. Okay? If we look down here and we plot voltage versus time, and then on that same graph, we plot current versus time, the voltage graph is going to take a sinusoidal wave, and the current is also going to be a sinusoidal wave. These are going to have the same time function. Okay? They have the same periodicity, which means they repeat in the same exact amount of time. These waves are said to be in phase. Does anybody know what in phase means? Yes, they do have the same phase constant. What's a phase constant? Yes, okay. Where did you guys learn that?
He liked phase constants.
Okay, that's actually really great. Phase constants are annoying. Most people who enter this class don't know phase constants. So these are in phase, okay? It means, as Zane said, phi s is equal to phi of the resistor. Okay? So that's kind of fun. Now things change a little bit when we go into look at a capacitor. So here we'll do KVL, KCL again. What you see is Vs is equal to Vc, and then Is is equal to Ic. So since this is a voltage-driven circuit, Vs is equal to Vc. We can write out Vc as the integral of 1 over C times Ic dt. Okay? Now, because we know that Vs is some function of a sine curve, what that ends up meaning is that if Vs is something like, I don't know, we'll just say it's R sine omega t plus phi, what that means is that your Vc is going to be equal to negative 1 over C R sine, well, your current is going to be equal to no, my bad. Ic is going to be equal to negative. Wow, now I suddenly can't do the math. Actually, I have to write this out. So here Ic would be equal to C dVc dt, which is equal to C dVs dt. So since that's the case, then Ic is going to be equal to C times R cosine omega t plus phi. And then here what we can do is we can play with a fun thing where we have this principle where sine of omega t plus phi is equal to cosine of omega t plus phi minus 90 degrees. I think that's it. Let me grab my book real quick. I just want to make sure I'm teaching this right. Yeah, it's, I can't remember if it's a plus or minus though. Because I am super good at remembering this part. Yeah, it's sine of this is equal to cosine of this minus 90 degrees. Okay? So, what does that mean? Well, if we take this principle, what we see here is this is equal to CR times sine of omega t plus phi minus 90 degrees. And then what you have here is because of that minus 90 degrees, if we go ahead and plot these, where our voltage is an oscillating input source, and then we have our current. What you end up with is, because this is a sine function and because this is a cosine function, these are no longer in phase. Okay? And what is said about this is, you'll notice the peak for the current precedes the peak for the voltage. So here it's said that VC leads, nope, IC leads VC. Because it reaches the peak before VC does. Okay, so that's fun. Now if we go on to the third, here we have the same exact set of equations. Vs is equal to VL, Is is equal to IL. Here, Vs ends up being equal to L DIL dt. Okay, so here if we turn around and solve this for IL is going to be equal to 1 over L. This is where we have the integral of Vs dt. Okay, so if Vs takes on the same form, which that is here, some value of R sine whatever, then what you end up with is that IL is equal to 1 over L times, well, it ends up being what? Yeah, 1 over omega L times cosine, negative cosine, omega t plus phi. Okay. So that's assuming that it has the exact same time function as this, which I should put the R in here because apparently I wanted to use R. I don't know why I would pick the letter R. That was a terrible idea. R was a bad idea. Whatever. In this course, R usually means resistance. I just used R as a constant. That makes sense. So we use the same phase shift principle to now flip this around and say that cosine of negative 90 degrees is equal to negative cosine of 90 degrees. Okay, so what does that mean? Well, it means we can rearrange this and write this as IL is equal to R over omega L sine of omega t plus phi plus 90 degrees. So when we plot out voltage versus time for an inductor, once again, assuming we have an oscillating voltage input, what you end up with for the current is that the current reaches a peak after the voltage. Okay? So what is said here is that IC lags VC. So here over here in the voltage, IC leads VC. Here, IC lags VC. Now you can flip that around, and you can also say that VC leads IC, and that VC lags IC over here. So it's just, you flip them around, it flips the terms. Okay? All right. Any questions on why the voltage and current have different phase angles? Okay, sweet. So we're going to take this principle and now we're going to look at a circuit where we're looking at steady state behavior Now we'll go ahead and plug two components in together. We'll just pick a simple RC circuit. Okay? Now we know from this circuit, because they're in series, this one is going to be VR is in phase with IR. But then we also know that VC lags IC. We know both of those at the same time. Okay? Well, that poses a problem for us because we know that VS has to be equal to VR plus VC. That has to be true at all times t. And because these are in series, we also know that IR has to be equal to IC, which has to be equal to IS. Okay? So this creates a very complex situation where this cannot be in phase because we have a capacitor. But on the flip end of that, it can't be 90 degrees out of phase because we have a resistor. It's kind of gross. Let's see. I don't really want to go through and derive everything. As much fun as that is, it's really not that much fun. We're going to introduce some terms that's going to make this, this analysis process a little simpler. Okay? Rather than go through this problem and try to derive it with integrals and derivatives and sit here and have a good laugh wearing my elbow patches and my... Look at how smart we are. Let's not do that. Although I can laugh like that anytime I want. I'm a professor. Huh?
What do the elbow patches have to do?
Well, it's what professors wear. That's why I'm not a real professor. That's also why I'm glad your sister didn't sit in on this class. Is this engineering? What is he doing? Yeah, I know, right? She goes home and she has to go see a therapist right away. Thanks, Mom and Dad. Yeah. Okay. So, I am going to introduce something called a phasor. Okay?
Light phasor.
You gotta set your phasors to stun right now. It's the only Star Trek I know. I'm terrible. All I do know the beam me up Scotty. But then Scotty wasn't even in like any of the other Star Treks. So it's kind of a weird thing to say. People get mad at you when you say beam me up Scotty and it's in the wrong Star Trek. All right, so I'm going to introduce the concept of a phasor. Now, all this is I'm going to write Vs is equal to A1 sine omega t plus phi. Okay? That's going to be my general equation for a sine curve. It has some amplitude A1. It has some frequency omega. It has some phase angle phi. So I'm going to write that out. Does anybody need me to go over what amplitude and frequency are? Heck yes! Makes life so much nicer. This is an angular frequency. No. Shut up. I backhand you. And then I turn around and I backhand you with the other hand. Again, glad your sister's not here. Angular frequency has units of 1 over seconds. Here, omega is equal to 2 pi over t, which is the period, or is equal to 2 pi f, where f is the frequency. Okay? And then phi, this is the phase angle. And all the phase angle does is change the phase. It's just a phase. Come on. Okay. Now I'm going to go ahead and rewrite this because everything in this system at steady state, we're going to be dealing with everything that has the same frequency. Okay? Which means that at steady state, all components in a circuit oscillate at the same frequency. Okay? Now what does that mean to an engineer? It means this. We don't care about omega. Nope. The only place where omega shows up is in a derivative or an integral. Okay? Because we don't need to write this piece out. This piece is going to be identical for every single component. So, we write this in a simplified format. When we write a phasor, we write this like this. A1 angle phi. Because we cut out that middleman. We don't need this piece, which is the same for every component. So we only focus on the two pieces that are different. A1 and phi. Okay? So, these statements here those are really long equal signs. Those statements are equal. It's just a simplified format of writing a sine curve. Okay? So for a phasor, if you see an amplitude, an angle, and then an angle, it's a way of writing a phasor, it's a way of writing a sine curve. Okay? This is very common in any kind of AC system that is being analyzed by an electrical engineer. So, we're also going to define the term root mean square. This is another term that just helps us, I guess, identify terminology. Here, if you have Vs is equal to A1 sine omega t plus phi, if you want to be able to, I guess, write this as a constant, okay, or do any kind of power calculations, doing power calculations over a continuously oscillating circuit can be really hard. So we want to write power, and to write power, giving an oscillating circuit, the power will oscillate. Yes. Problem is, the power also oscillates with current, and if we're dealing with a non-resistor component, that means that our current and our power and our voltage are going to be out of phase. So what we can do here is we're gonna simplify this down to an average value that happens over a single sine wave. Okay? Okay, and here this is going to be an average absolute value of a voltage. I should, I guess, write absolute value. Okay, if we know that, it allows us to better calculate power. Okay? So the equation for a root mean square is given by V RMS is equal to the square root of 1 over the period times an integral from 0 to the period of the square of the voltage with time. Okay, why are we doing a square root of the square? It's because it gives us that absolute value. Okay. Now, as I said, when it comes to AC systems, we don't really want to have to do integrals. So when it comes to a sinusoid, which is most of the time what we're dealing with when it comes to AC, a sinusoid is just a sine wave. You could have a square wave, you could have a sawtooth wave, you could have a bunch of different types of waves. And all it does is it changes this value, you can actually find VRMS, the equations for all of those online, which would be way easier than deriving them. But for a sinusoid, VRMS is equal to VM. A1 times, well, this is A1 over the square root of 2. Okay? That's it. Which, that's a lot easier to calculate than going back through and trying to identify power here. Now, the nice piece about this, too, is that IRMS for a sinusoid is also equal to whatever the value of A is for current. I'm just going to write that as I over the square root of 2. I mean, the calculation stays the same. So, if you multiply these two together, what you end up with is that power is, it's just equal to one of these times the other divided by 2. So, that's kind of nice. Eee. Okay, so now we haven't really done any real math yet. We've introduced some terms. We've looked conceptually at some at some systems, how they behave. We're going to take the concept of phasors. We're going to take the concept of root mean squares, and we're going to go ahead and plug that in and do some math. But we'll do that in the next class. So I'll see everybody back here at 9:10, and we'll keep going from there. So.